Let's work out problem number one from our problem sets. This problem number one in our problem set asks you to solve this differential equation, but I added a little extra to it. I want our solution to the differential equation to also satisfy this initial condition that when we plug in 0, we get 3 for our y value. So we can divide both sides by y squared to get 1 over y squared dy dx is equal to x. And again, well, at the moment, we have on the left-hand side this to be solely a function of y, this to be solely a function of x. So we know that this is a separable differential equation. And whenever you have a separable differential equation, again, for simplicity, we're going to think about that dy dx as if it were a fraction, where the dy is the numerator, the dx is the denominator, and we can multiply both sides by dx to get 1 over y squared dy is equal to x dx. Again, the benefit of this is that it gives you a gigantic shortcut for doing the computations. So we can take our current equation and take the antiderivative of both sides on the left-hand side with respect to y, on the right-hand side with respect to x. The antiderivative of 1 over y squared is negative 1 over y plus a constant. The antiderivative of x is 1 over 2 x squared plus a constant. And I'm going to take the two constants from the left-hand side and the right-hand side and move them all over to the right-hand side and account for them with one single constant plus c. At this point of our problem, it would be a good idea to bring in that initial condition and figure out what the value of c is. So again, we have y of 0 is equal to 3, so we have the point 0, 3 as a point on our solution. So when you plug in 0 in for your x's, you should get a 3 for your y's. Solving for c, we get that c is equal to negative 1/3. So you have the equation negative 1 over y is equal to 1/2 x squared, and our c is negative 1/3. So this is an equation containing the solution to our differential equation. We're going to ask ourselves, can we solve for y in this equation? And we most certainly can. Let's do it one step at a time. Let me get rid of that negative 1 in front of 1 over y by multiplying both sides by negative 1. So you got 1 over y is equal to negative 1/2 x squared plus 1/3. Then if I take the reciprocal of both sides, I get that y is equal to 1 over negative 1/2 x squared plus 1/3. And this is the solution to the differential equation. So if I take this function and take its derivative should be equal to x times that function squared. One thing to note is that this is a first-order differential equation, and in the previous sections we talked about how to use a slope field and a computer graphing utility to help us visualize what the solution should look like. So let's go ahead and call up GeoGebra, and that's the slope field generated from GeoGebra, and see what the solution should look like for dy dx equals xy squared. So again, you can call this up by going to Google and typing in slope field generator, and it's like the second option. And again, in our y prime being our dy dx, I'm going to write our xy squared. Press enter, and there you go. You can play around with the density, how many of these line segments you have. You can play around with the length, how long each one of these line segments will be. And moreover, you can play around with plotting a point on this interface. And again, we want our solution to have the point 0, 3. So I can take this red dot right here, carry it over to 0, 3, somewhere around there. Close enough. This function looks a bit parabolic. Let me see if I increase this to maybe a 15, if I get something that looks more interesting. Nah, it doesn't look all that much interesting. Let me play around with some of these values and see if I can make this look nicer. All right, well, that's what it is. So the solution to this differential equation looks almost like a parabola that opens upwards, right? We could go and use Desmos, www.desmos.com, and graph our function and see if our function looks like what we expect it to be. So I'm graphing the function y equals the fraction of 1 over negative 1/2, negative 0.5, x squared plus 1/3. And around the neighborhood of 0, 3, here is the graph that we're considering. Note that when we graph out our solution on Desmos, Desmos gives us some extra points that are not being represented in our slow field generator. If you look at your function, consider that this denominator will be 0 when x squared is equal to 2/3. That is when x is equal to either plus radical 2/3 or negative radical 2/3. So at plus or minus radical 2/3, you have some vertical asymptotes. That means that your function doesn't exist at those points. And if it doesn't exist, then it definitely can't be differentiable at those points. And once it stops being differentiable, then you wouldn't care about including any points to the left of those numbers or to the right of those numbers, because in order for you to have a solution to this differential equation, you have to have a function that is differentiable. So that's why when we graph out our differential equation on the slow field generator, it only graphs out the middle, because it's deleting what's going on the far left, it's deleting what's going on the far right, because we have these vertical asymptotes giving us a break, and we can't include the stuff on the left or the right because we want to have only a function that is differentiable. And that's why we only include the elements in the middle.